Good morning. Today's lesson is on Newton's law of cooling. Newton's law says that the temperature of a liquid, or anything actually, will reduce at an exponential rate until it reaches the ambient room temperature. That exponential rate actually depends on the actual item that's being cooled, but today we're going to look at a specific thing. Well, we're going to, not specifically, just hot liquid. So the bell ringer starts with, how hot is a cup of coffee? Now, I get my coffee daily, and I try to keep it hot in this little thing right here because of Newton's law of cooling. If I were to have it in a regular cup, it would cool a lot quicker. This actual cup keeps it warmer longer, and that's the reason why I put it in there. So fresh out of the pot, it really depends on when that pot got off heat. So, but how long would that cup of coffee take to cool down to room temperature? Would the temperature of the cup of hot coffee change at a constant rate? So, like, would it change, reduce temperature a degree every minute or something like that? And if so, why? If not, why not? How do recursive rules compare to explicit function rules when the relationship is exponential? We kind of looked at that in the last lesson, comparing models. And what does it mean for a relationship to be proportional? So we'll look into all of that. How hot is a cup of coffee? This bell ringer just is to make you think, because the whole lesson is based on this specific topic. How fast does a hot liquid cool? So what's making life great? Today I'm leaving for a tennis tournament in Madisonville. Well, not today. When you see this lesson, it will be the following day. We'll see how that goes. We've got a lot of kids playing, a lot of kids that aren't varsity. This is not a varsity tournament, but that's all right. We should do pretty well. We'll see. Share with me via email or anyway, even personally if you want to, about things that are going great in your life so that I can share them with your fellow classmates. It'd be great. So let's get on with this lesson. All right. So here's the problem. Have you ever noticed that a container of cold liquid, such as a glass of iced tea, creates condensation on the outside of the container? What do you think that is? Most likely, the outside of the container is colder than the actual temperature of the air, and the moisture in the air is drawn to it because it is below what we call the dew point. It causes the moisture in the air to form on the outside of the glass. It's not from the glass at all. It's from the air. The air's moisture is it's like almost like getting called to attention and brought there. So anytime air comes close to it, that moisture gets drawn to it. It actually helps that water on the inside warm up to room temperature. How about a cup of hot coffee? How come it doesn't always stay hot? That's because the steam of it comes out of it and causes the liquid to cool off to get down to room temperature. What happened to the temperature of those cups of liquid? Well, in this activity, we're going to investigate changes in temperature of a liquid over time. Now, in the past, I've attempted to measure the change of a cup of coffee over the course of a period. 55 minutes is not long enough to show or prove that the liquid goes down to room temperature. If I were in a block scheduling where I had more than an hour in class, maybe 90 minutes, I might be closer to it. But generally speaking, a lab of that nature needs to be presented for an entire day, and that's difficult to do. So I don't do that anymore. I don't even try. I'm just going to give you some examples of how to look at it. So if your teacher poured a cup of coffee at the beginning of class, set it on her desk, and forgot about it, what would happen to the temperature of the coffee over time? Why do you think this is so? Well, we'll sketch a graph of the coffee's temperature. This is just an estimation of what might happen. Now, this is not accurate. This is just your teacher's rendition of what he thinks might happen. And actually, if temperature is the y-axis and time is the x-axis, the temperature would go down at some curve similar to this over the course of time. All right, so this is a table that shows the change in temperature L of a cup of liquid over time T. We're going to complete this table by computing the first differences and successive ratios. Remember in the last lesson we looked at the successive ratios? So what we're looking at is the differences, or the comparison of the two differences, and dividing them one after the other to determine things. So the difference between the temperature from 60 to 58.72 is minus 1.28. Temperature went down 1.28 degrees, okay? Now, if we divide this 58.72 by 60, we get 0.9786666. We'll do the same thing for the next one. Temperature went down the exact same, got the same or very close to the similar ratio. 57.44 divided by 58.72 nets us 0.9782016. And we can continue with this, and as you can see, the change in the temperatures is reducing. It doesn't go down as much every minute. As a matter of fact, after 9 minutes, the temperature is going down only a degree a minute. And then in that 10th minute, it's less than a degree. We can continue this process for a while. But as you notice over the course, and let me move my face here. It doesn't want me to move. Over the course of 12 minutes, we have reduced from 60 to 46.94, or the equivalent of about 17 degrees. So let's look at this a little better. Now, if you see the changes in the temperatures are going down, but the successive ratios, the difference or the temperature of 1 minute divided by the minute before is essentially the same throughout the process. So, is the relationship between time and temperature linear or exponential? If it were linear, all of these differences would be common, but they aren't, are they? So if they were all minus 1.28 all the way down, then it would be a line. The temperature would go down in a linear fashion. But because the temperature goes down and the change in temperature changes, we call that something different. It's not linear. It's no longer linear. But the successive ratios are the same. Now, the successive ratios, this amount that we multiply by this temperature to get this temperature, it is nearly the same in every single change in temperature. So the relationship is exponential because the first differences are not constant, but the successive ratios are nearly constant. So, move my mug again. It does not like me to move. Use the information in the table to build a recursive rule for the differences in temperature from room temperature for each successive temperature reading. So, successive ratios is calculated by finding the quotient of the current divided by the previous temperature. The current temperature divided by the previous temperature gives us a successive ratio. We do this for everyone. The temperature at time 4 divided by the temperature in time 3 is 0.9793667. It's the same thing. Successive ratio is the time currently divided by the time 1 minute before. And we can do math. Since we know the successive ratio is around 0.979, the new temperature equals the old temperature times 0.979, where the original temperature is 60 degrees and n increases by 1 starting at 1. All right, so what does a constant 0.979 in the recursive rule represent? Obviously, it represents the successive ratio, or the average common ratio that's multiplied by the previous term to generate the next term in the sequence. So if we go back to this term, if we were to add all of these up and then divide by 12, that's where we get this number, the average common ratio, okay, multiplied by the previous term, generates the next term in the sequence. Okay, we're going to use a graphing calculator to make a scatter plot of the temperature versus time. Now, I'm not going to pull my calculator up and do this. I'm just going to show you what it looks like. If this is time in minutes, and this is temperature over time, over the course of 20 so minutes, we can see that the temperature is moving in a curve, not a line. It looks nearly linear, but you can see a semblance of a curve to it. And if you were to look closer and closer, you'll notice that over the course of a long period of time, that will actually curve and bottom out somewhere. Where do you think that bottoms out at? We'll discover that in one of the next slides. Does the scatter plot support the type of relationship you chose earlier? Yes, it does. It shows the graph that is decreasing at a non-constant rate. Okay, the general rule for the exponential function is y equals a times b raised to the x power. A represents the initial condition, B represents the successive ratio or base of the exponential function. Using data from the table, let's write a function rule that describes the temperature of the coffee Y as a function of time X. Y equals 60 times 0.979 raised to the X power. 60 is the initial value of the temperature. 0.979 is the successive ratio. But as X rises to infinity, it means that the temperature goes down to 0. And 0 Celsius is freezing. But what if the temperature outside is not freezing? What temperature does it go to? Okay, what does a constant 60 in a function rule represent? Obviously, it's the initial temperature, and the 0.966 represents nearly constant successive ratio of temperature measurements. Now, the ambient room temperature needs to be considered when making the function of this situation. When we do consider this, the initial temperature is not used in the function. Instead, we'll use the difference between the initial temperature and the ambient room temperature instead of the initial temperature. Even then, we still must adjust the temperature function by adding the room temperature to the end of the function to create an appropriate representation of the actual function. And you'll see what that looks like here. If the initial temperature is 60 degrees and room temperature is 21 degrees, the difference is 39 degrees. So the actual explicit function is the temperature currently, which is T subscript n plus 1, equals the difference between initial temperature and room temperature, times R, which is the successive ratio, raised to the T. And then we're going to add room temperature to it. T is the temperature at time T, IT is initial temperature, and RT is the room temperature. All right, this is our function using the information we have, where IT is 60 degrees, RT is 21 degrees, and R is 0.966. We just look at it, and we can actually do the math on it. But I'm going to launch this with you. In 1992, and I recall this happening, a 79-year-old lady won a lawsuit from McDonald's because she spilled a hot cup of coffee on herself. And I can't make this up. I had to write a report for this in my ethics class when I was going to school for my master's degree. The age of the lady was 79 years old. She spilled the coffee in her lap, and the coffee's temperature was 180 degrees. Now, at 180 degrees, liquid will give you an automatic second-degree burn. Because it's not burning like a coal, it can't give you a third-degree burn, but a second-degree burn, and she suffered second-degree burns on 15% of her body, and it was in her lap. Okay, so the reason McDonald's gave for their temperature of the coffee, they wanted to ensure our customers' coffee remained hot throughout their commute to work. The amount of the settlement is $2.4 million. Now, I can't make this up. I've actually left a link here on the slideshow, which you'll get a link to the slideshow in the Google Classroom, showing the facts to this particular case. So anyway, there's a lesson in the Google Classroom. Be sure to do that assignment. And in the meantime, be blessed, be a blessing.